this question, we're given that of all numbers whose difference is 12, find the two that have the minimum product. So we're given that the difference, I'll write that as D, is 12. We want two numbers, so we'll call one number X and one number Y, and we want them to have a minimum product, and we're told the difference between those numbers is 12. Well, difference can be written as X minus Y, or you could write it as Y minus X, but I'll say X is the bigger number. So X minus Y is 12. So let's put these together. So we know that X minus Y is 12, because we want their difference to be 12, and we want to find the minimum product. I'll also use P for product. A product of two numbers means multiply the numbers. Since our numbers are X and Y, we'll say their product is X times Y. So we want to minimize this product, but we can't minimize something with two variables in it, at least not with the techniques we know so far. So what we can do is we can rewrite this first equation, X minus Y equals 12, and solve it either for X or Y, and then plug that in to our product formula. So because it's easier to solve for X, I'll solve for X. So here we have X equals, I add Y to both sides, we have 12 plus Y. So now we can plug that in to our product equation. So instead of X, we'll plug in 12 plus Y. So that means our product, instead of X, it's going to be 12 plus Y times Y, where the first factor is X and the second one is the Y. Let's distribute this so we can more easily find the derivative. So let's see, 12 times Y is just 12Y, and Y times Y is just Y squared. So in order to find the minimum product, we need to find the critical point. So to find critical points, we take the first derivative. So let's find the first derivative of this product, and that's just going to be with respect to Y. So it's 12Y, the derivative of that is just 12. The derivative of Y squared would just be 2Y. Now let's find where this is either undefined or equal to 0, because that's how we find critical points. Because this is never going to be undefined, I'll just set it equal to 0 and then solve for Y. So solving for Y, we subtract 12 from both sides, divide by 2, and we get that Y is equal to negative 6. Now if Y is equal to negative 6, we know we can just plug that in. We know that X is equal to 12 plus Y, so that means X is equal to 12 plus negative 6, that's 12 minus 6, which is 6. So that's our two numbers. So our two numbers are negative 6 and 6. However, we don't really know this is our final answer until we check concavity. These could be two numbers that give us a maximum product instead of a minimum product. So let's find the second derivative. And alternatively, you could use the first derivative test here. So if we find the second derivative, that's just finding the derivative of our first derivative. Our first derivative is 12 plus 2y. The derivative of 12 is 0. And the derivative of 2y is just 2. Since this is greater than 0, that means our function is concave up at that critical point, which means that we do have a minimum. So in other words, our product is indeed minimized when one of our variables, one of our numbers, is negative 6 and the other one is positive 6. So we have a minimum product. Well, the product is just the multiplication of those numbers, so our minimum product is negative 36 when one of our numbers is 6 and the other is negative 6. Let's do another optimization problem, a little bit more applied. So in this example it says, a farmer has 1,200 feet of fence and wishes to build two identical rectangular enclosures, as in the following figure. What should be the dimensions of each enclosure if the total area is to be maximized? So in our example, we're given this picture here. So we have a rectangle that's divided into two equal rectangles. and we want to maximize the area. And I'll use A for area. We weren't given any variables to work with. We were also told the perimeter of, well, really I shouldn't even say perimeter, that the amount of fencing, I'll use P because it's almost like a perimeter, the amount of fencing has to be equal to 1200. So let's put some variables together to work with here. So we want to try to maximize the area subject to the idea that we only have 1200 feet of fencing to work with to make this shape. Well, we were told these two rectangles were identical. So I'll call the height of each of these rectangles y. So we have three y strips of fencing. And then we have an x here and x here because they have to be the same shape, and an x here and an x here. So together, if we put this together, we're given that we have to have, well, 4 x strips of fencing plus 3 y strips of fencing, and in total this has to be 1200 feet of fencing. We also want to find the area of the shape. Well, the area of a rectangle is just length times width. The length of a rectangle, well, it's 2x wide. So our length is just going to be 2x, and the height we already figured out was y. So we want to try to maximize this area when we only have 1200 feet of fencing. Well, we can't maximize with two different variables, so what we can do is we can rewrite this P equation, the amount of fencing we have. Maybe we'll solve this one for y. So if I solve this for y, just subtract 4x from both sides, I get 3y equals 1200 minus 4x. Then I can just divide both sides by 3, and I get that y is equal to 400 minus 4/3 x. And so we have fractions, but that's all right. Let's take this value for y and plug it into the area. So now we only have one variable in our function. So it'll be 2x times y, but y is just 400 minus 4/3 x. Since ultimately we're going to take the derivative, let's distribute this 2x so we can work with it a little bit more simpler. So let's see, a is going to be equal to 2x times 400 is 800x, minus, let's see, 2x times 4/3 x, well, 2 times 4/3 would be 8/3, and x times x is x squared. So to find the critical points, which if there is a maximum, that's where it will occur. So let's find this derivative. Let's see, 800x, the derivative of that would just be 800. Minus, okay, drop the 2 down, that gives us 16/3 x. Next we want to find where this is either equal to 0 or undefined, but since it's linear, it's never going to be undefined, so we'll just set it equal to 0. Then we just have to solve for x. We could add 16/3 to both sides, so we have 800 equals 16/3 x. I'll just multiply both sides by 3, and I get 2400 equals 16x. Divide by 16, and that gives me 2x equals 300, I believe. Divide by 2, and we get that x is equal to 150. So if x is 150, we could figure out what y is. We know y is 400 minus 4/3 x, so that'd be 400 minus 4/3 times 150. So that means y is equal to 400 minus, let's see, 150 divided by 3 is 50. 50 times 4 is 200. So that means y is equal to 200. So if this is a maximum, that means that the maximum will happen when x is 150, so each corral is 150 wide, and 200 feet tall, or long if you want to say it that way. Alright, to verify that this is indeed a maximum, we have to do the second derivative. So let's find the second derivative, because remember this could be where it's a minimum possibly. This might be what minimizes the area. So finding the second derivative derivative of our first derivative of 800 is 0, derivative of negative 16/3 x would just be negative 16/3. Since this is less than 0, that means our function is concave down, which means this is a point that will maximize the area. So therefore, we could say that the absolute maximum area occurs when each enclosure is 150 feet by 200 feet.